Hello everyone, welcome back to ShowOffer.io. We are helping you master system design for big tech interviews. If you're aiming for a role at OpenAI, Meta, or any top-tier tech company, there's a high chance you'll face this question. How would you design Yelp or a point of interest application? Now, if you've been following our series, you'll remember our previous episode on proximity problems, where we discussed the fundamental challenges of designing systems that operate based on a user's location. Well, today, we're zooming in on one real-world application of proximity problems, designing Yelp. Think about it. You're in a new city, hungry, and looking for the best-rated pizza nearby. You open Yelp, and within seconds, it shows you a ranked list of restaurants, all sorted by distance, ratings, and even whether they're open right now. So, how does Yelp do this? How does it efficiently find and rank places near you among millions of businesses worldwide? This is where proximity-based search meets large-scale system design. At its core, applications like Yelp, Google Maps, and Uber need to store and retrieve millions of location-based businesses efficiently, run real-time proximity queries to find the best results instantly, handle real-time updates when businesses move, close, or get new reviews, scaled to millions of users per second without breaking down. But here's the key takeaway. Yelp is just one example. The same geospatial techniques power Uber Eats, ride-sharing services like Lyft, and even emergency response systems like ambulances and fire dispatch. So, in today's episode, we're going to tie everything together. What are the functional and non-functional requirements of Yelp? What is the high-level design with explicit API requests and responses? What are the functional workflows with logical components? How Yelp can perform robust and efficient in large-scale requests. This is a frequently asked interview question at Meta, OpenAI, and other top tech companies. So if you're prepping for interviews, this episode will give you a strong, structured approach to tackling it. By the end, you won't just understand how Yelp works. You'll have a clear framework to answer any proximity-based system design question confidently. All right, let's get started. All right, now that we've set the stage for Yelp as a proximity-based system, let's break down the requirements. Because any good system design interview starts with understanding what we're building. For Yelp, we can categorize requirements into two main areas. Functional requirements, what the system should do. Non-functional requirements, the constraints that ensure the system performs well at scale. Let's go through them one by one. Functional requirements. What should Yelp be able to do? At its core, Yelp is a search and review platform for local businesses. That means it needs to support 1. Search for businesses by location. A user should be able to search for businesses based on city or address. For example, coffee shops in downtown Seattle. GPS location with a radius filter, for example, restaurants within 1 mile, or gas stations within 500 meters. Additional filters like name, category, or whether the business is currently open. Second functional requirement is that users on Yelp can view business details. Once a user finds a business, they should see name, address, contact details, business hours, user ratings and reviews, photos uploaded by users or the business owner. The third functional requirement is users can leave a review. Users should be able to rate a business on a 1 to 5-star scale. Write an optional text review. Attach photos, optional, to provide visual context. These three core functionalities, searching, viewing, and reviewing businesses, are the foundation of Yelp's system. Let's come to the non-functional requirements. How should the system perform? Since Yelp operates at a global scale, the system must meet several performance and reliability guarantees. First, high availability. Availability greater than consistency. The system should always be available to serve user requests for searching, viewing business details, and submitting reviews. Eventual consistency is acceptable for things like reviews. If a new review takes a few seconds to appear for everyone, that's fine. Second, scalability. The system should handle 10 million businesses and 100 million monthly active users. This means Yelp needs efficient geospatial indexing and a distributed architecture to keep response times low. In addition, the system should perform low latency in search. Searching and viewing business details must be fast. Users expect results within 1 second. Since reads are much more frequent than writes, we should optimize for fast queries and caching. Fault tolerance is also a non-functional requirement. The system should remain functional even if some components fail. For example, if one database node crashes, users should still be able to search and read reviews. And finally, the compliance, where one review per user per business should be constraint. Each user should be allowed to rate a business only once. This prevents spam and ensures review authenticity. There are some additional below-the-line requirements. These aren't our primary focus, but they're worth noting. Business owners should be able to manage their listings, add, update, or remove businesses. Personalized recommendations based on user activity could improve engagement. User authentication and identity management, as known as IAM, will be needed for reviewing and rating businesses. All right, that wraps up our requirement analysis. To summarize, Yelp is a read-heavy system that prioritizes fast searches with a radius filter. It needs to scale to millions of businesses and users while maintaining high availability and fault tolerance. Eventual consistency is acceptable for reviews, but search results must be instant. Now that we understand the requirements, the next step is figuring out what entities and APIs we need to build this system. Now let's dive into the core entities of Yelp. Because before we start designing APIs or storage, we need to understand how data connects and flows through the system. At the heart of Yelp, we have 3 key entities. First entity is user. These are the people using the platform. They can search for businesses, leave reviews, and rate places they've visited. Each user has a profile that stores their name, preferences, and activity history. The second entity is business. Every restaurant, coffee shop, or local store listed on Yelp is a business entity. A business has details like name, address, contact information, operating hours, and a category. For example, Italian restaurant. Businesses don't generate content on their own. They rely on user-generated reviews. Third entity is the reviews, the connection point between users and businesses. Every review belongs to one user means the person who wrote it, one business where the place being reviewed, and a rating from 1 star to 5 star with optional text, and sometimes with optional photos or media files. Let's take a look into the connections between these entities again. Users interact with businesses by leaving reviews. Businesses accumulate reviews, which influence search rankings and recommendations. Each user can only review a business once, ensuring data integrity. This forms the backbone of Yelp's system. Every feature, search, recommendations, and ranking, relies on how these 3 entities are structured and queried efficiently. Now that we've defined our core entities, users, businesses, and reviews, it's time to talk about API design. In a system design interview, one of the best ways to show clarity and completeness is by ensuring that each functional requirement has a corresponding API design. This not only demonstrates a structured approach, but also helps interviewers assess how well you can break down system interactions. APIs define how clients like mobile apps or web apps interact with the backend system. A well-designed API should satisfy 3 points. Number 1. Efficiently expose core functionality such as search, view details, and write reviews. Number 2. Be intuitive and easy to use for front-end and third-party developers. Number 3. Handle scale and performance constraints. For Yelp, we need at least a 1-to-1 API mapping with our functional requirements. Let's break down the 3 core API endpoints. API number 1. Search for a business with pagination. This API allows users to search for businesses near a specific location. Here is the API endpoint and the request parameters. Term means search keyword, for example, pizza, coffee, gym. Location usually composites with latitude and longitude, and it is suitable for GPS-based search. Radius means search radius reference to the geolocation where user has centered, for example, 1,000 meters. Category is optional, which is filtered by business type, for example, restaurants, barbershop, etc. Limit means number of businesses per page, and offset indicates how many results to skip, for example, for page 2. If limit equals 10, then offset equals 10. This is a general combination for pagination in search results with only partial list of entities to return. Let's come up with an example. Request. This request asks to F and pizza places near New York, where GPS of New York is 40.7128 north, 74.0060 west. Asks to S how only 10 results per page, and S keep the first 20 results, meaning we're fetching page 3. This assumes page 1 equals offset 0, page 2 equals offset 1 patavde. And here is the response. The API returns a list of businesses matching the search query and location. The radius filter ensures that users get relevant nearby results. The response includes business details, ratings, and open status for quick decision-making. You may want to ask how pagination works in search. The pagination object in the response tells the front end, for example, limit equals 10. Each page contains 10 businesses. Offset equals 20. This response contains results starting from business number 21. Total results equals 254. There are 254 total businesses, so the front end can calculate how many more pages exist. For infinite scrolling, the front end can increment the offset. Next offset equals current offset plus limit, and load more businesses dynamically. For next page buttons, the front end can track the total results and ensure users don't request beyond the last page. The second API is to view business details. This API retrieves detailed information about a specific business when a user clicks on it. Here is the API request, where business ID is the unique ID of the business, and here is the response. This API returns complete business details, address and contact info, ratings and user reviews, business hours and open status, photos uploaded by users or the business, etc. This API is critical for users deciding where to visit, order food, or book a service. The third API is to submit a review for a business. This API allows users to leave a rating and optional review text photo for a business. Here is the API endpoint and request body. And here is the response. Users must be authenticated, hence the JWT token to leave a review. The rating is mandatory, but text and photos are optional. The system enforces the one review per user per business rule. If a user already left a review, they should only be able to edit it, not submit another one. This API is write-heavy, but we optimize for quick response while processing review data asynchronously. So, to summarize, Search API helps users find businesses near them quickly. Business details. API gives complete information about a business. Review API allows users to rate and review businesses. These three core APIs cover Yelp's primary user interactions: searching, viewing, and reviewing businesses. Now, we are coming to the high-level design part. The core idea here is to map every functional requirement into a working solution based on our API design with entities. Let's talk first about searching for businesses by location. Here is the basic flowchart for search. At first glance, this seems straightforward. A simple database-backed CRUD service should get the job done. The workflow is fairly simple. The client sends a GET request to search for businesses using specific parameters. These might include finding businesses within a 1-mile radius, filtering for those that are currently open, or sorting results by average rating to highlight the best options. Once the request is made, it first goes through the API gateway, which is responsible for routing traffic to the appropriate backend service. In this case, the Business CRUD service handles the request. This service queries the database, retrieves the matching businesses based on the search criteria, and returns the results to the client. At a small scale, this setup just works. It's a simple request-response interaction where the client gets a list of businesses that match the given parameters. But as we scale, challenges start to emerge. Efficiently handling geospatial queries, optimizing response times, and ensuring the system remains performant under heavy traffic. As of high-level design, we already provide enough details. We will leave deep dive discussions later for performance optimization in databases. Now let's talk about the second functional requirement. User can view business details. Once a user performs a search, they receive a list of businesses that match their query. Each business in the result contains basic metadata like its ID, name, distance, rating, and category. When the user clicks on a business, their app sends a GET request to the backend service to fetch detailed information about that specific business. On the backend, the Business CRUD service receives the request and queries the database using Business ID. Since this is a read-heavy operation, we need to ensure fast response times by leveraging proper indexing and caching later. But as of high-level design, it is a working solution. Once the service retrieves the business data, it returns a detailed response to the user. This response typically includes exact location, address, latitude, longitude, contact information, phone number, website, operating hours, whether it's currently open or closed, aggregate rating, average star rating from all users, business attributes, like whether it offers delivery or has outdoor seating, menus or service offerings, if applicable, recent reviews, specifically the 10 most helpful or critical ones, to help users make an informed decision. The reason we fetch only a limited number of reviews instead of all reviews is performance optimization, similar to the partial list return from searching business. Reviews can be paginated as well, and additional reviews can be fetched on demand if the user scrolls down. Now let's talk about the third functional requirement, leaving a review. Leaving a review is a key feature of Yelp. It allows users to share their experiences and helps others make informed decisions about businesses. Here is the high-level design for posting a review. User submits a post request to the backend with their review details. This request is sent to the Business CRUD service. Once the review request reaches the backend, the service performs several validation steps. Such checks if the user is authenticated and has not already submitted a review for this business, validates the rating value to ensure it falls within the allowed range, 1 to 5 stars, and scans for inappropriate content, such as offensive language or spam, before storing the review. After validation, the review is stored in the review table of the database. Each review entry is linked to the user who submitted it, the business being reviewed, and a timestamp for when it was created. Once the new review is added, the system recalculates the average rating for the business. Instead of recomputing it from scratch every time, the system increments counters for total rating sum and total review count, then updates the business record efficiently. After the review is successfully stored and the business rating is updated, the backend sends a confirmation response to the client. And this is the functional flow for reviewing from users. Now we have already walked you through with the functional requirements in our high-level design diagram. It is a working solution, but far from perfect. In the next chapters, we will share more deep dives to make the whole system performant. Now comes to the part of deep dives. The deep dive is the most significant part that helps up-level your performance, especially for the staff plus level engineers. The best way to illustrate is that you can proactively to come up with deep knowledge on the optimization based on the functional high-level design with options comparisons. For our first deep dive point, let's talk about how we can keep the system with high availability and fault tolerance. Building a system like Yelp requires ensuring that the platform is highly available and fault-tolerant in the face of failures. Failures can happen at any time. Services might crash, databases could become unavailable, and network issues could interrupt communication between components. To maintain a smooth user experience, we must design resilient architecture that can recover from failures without significant downtime. In this deep dive, we will break down three major failure scenarios. First, service component failures, when a microservice crashes or becomes unresponsive. Second, database failures, when the primary data store goes down or becomes overloaded. Third, network failures, when communication between system components is disrupted. For each, we'll discuss the failure modes, possible solutions, and the best approach for Yelp's architecture. 1. Handling service component failures. In Yelp's system, we have multiple microservices, such as the Business CRUD service, Search service, and Review service, that need to communicate with each other. If any of these services fails, we must prevent it from bringing down the entire system. And here are some component failure mode. A microservice instance crashes due to unexpected errors. A service becomes overloaded and cannot process requests. Unhealthy instances continue receiving traffic, causing degraded performance. Several improvements can help make the change to prevent component failures. The first consideration is to use load balancing with auto-scaling. We can deploy multiple instances of each service across different availability zones. A load balancer distributes requests evenly, and if an instance fails, it redirects traffic to healthy instances. And using auto-scaling policies can spin up additional instances when traffic spikes to prevent overload. The second consideration is to handle graceful degradation with caching. If the Business CRUD service fails, we can return cached business details instead of throwing an error. This ensures that users can still view business listings, even if real-time updates aren't available. Third consideration is to apply retries with exponential backoff. If a request fails due to a transient issue, we retry the request with a backoff strategy. Instead of retrying immediately, we gradually increase the wait time between retries. This prevents overwhelming the system with repeated failed requests. These three considerations are the most commonly used and can be combined together for covering all the component-level failures during your design. Now let's talk about handling database failures. Since Yelp is a read-heavy system, the database must support millions of read queries per second while remaining highly available. But failures can occur when the primary database goes down, the system experiences high query loads, leading to slow responses, and a database shard becomes inaccessible due to a hardware failure. Here is the potential solution points to talk about during your interview. 1. Master-slave replication for high availability. Use read replicas to distribute read traffic and reduce load on the primary database. If the primary database fails, a failover mechanism promotes a replica to master. Second, database sharding for scalability. Instead of storing all businesses in a single database, we partition data across multiple shards based on geography. For example, businesses in New York in one shard, businesses in California in another. If a single shard fails, only a small portion of users are affected, not the entire system. Third, asynchronous writes with eventual consistency. New reviews and business updates don't need to be immediately consistent across all replicas. Instead of waiting for database synchronization, we use an event queue, like Kafka, to asynchronously process updates, ensuring the system remains responsive. Fourth, caching layer to reduce database load. Frequently searched businesses are stored in Redis. If the database becomes slow, Yelp can return cached results instantly. Fifth, retry mechanism with fallback strategy. If a query fails due to temporary database unavailability, the system retries it. If the primary database remains down, Yelp can serve stale data from the cache instead of throwing an error. Now let's talk about handling network failures. Even if our services and database are working fine, the network itself can fail. Failures can include packet loss causing delayed or dropped requests, DNS resolution failures, preventing services from communicating, and intermittent connection timeouts between front-end and back-end services. Here are some good considerations to mitigate such potential issues. First consideration is to apply retries with jitter, also known as randomized backoff. Network failures are often temporary. Instead of immediately failing, we implement a retry mechanism with a jitter strategy, introducing randomness in retry intervals to prevent request bursts. For example, if a review submission request fails due to a timeout, the system waits 200 milliseconds, then 500 milliseconds, then 1000 milliseconds, adjusting based on network health. Second consideration is content delivery network, also known as CDN for static data. Business images, cached search results, and popular listings are served via a CDN to reduce dependency on direct database requests. Even if a network failure occurs, users still receive business details from the cached data and edge locations. That's the part of deep dives and keep high availability and fault tolerance. Now let's focus on the latency improvement. For a heavy read system, latency can be improved from its data storage with indexing strategy, caching layers, read workloads, and pagination optimization. I will use these 4 areas to deep dive. For the first area, let's talk about data storage with indexing strategy. Here comes to the part where you can discuss in-database options. When designing Yelp's database layer, one of the most important things to consider is that reads far outnumber writes. The majority of traffic comes from users searching for businesses or viewing business details, while business owners and admins rarely update listings. Because of this read-heavy nature, our system must be optimized for fast search performance. Let's run a quick back-of-the-envelope estimation to understand the scale of this challenge. As of May 2024, Yelp has around 60 million monthly active users. To make our calculations more robust, let's round that up to 100 million users. Now, not every user is active every day. A reasonable assumption is that 20 to 30% of monthly active users engage with the app on a daily basis. That gives us somewhere between 20 to 30 million daily active users. Next, let's estimate search volume per user. On average, a typical user might search for businesses 2 to 5 times per day. Using that, we can estimate the queries per second. On the lower bound, if 20 million users each perform 2 searches per day, then the total number of queries per day is 40 million. Spread across 100,000 seconds in a day, that gives us a baseline of 400 QPS. On the upper bound, if 30 million users each perform 5 searches per day, that results in 150 million queries daily, translating to about 1,500 QPS. Considering the peak traffic is never evenly distributed. During peak hours, QPS could spike up to 3 times the average load. That means our peak load could reach around 3,000 QPS. This means our database layer must handle at least of read requests per second efficiently. A traditional relational database with basic indexing won't be enough at this scale. We'll need geospatial indexing, and there are 2 main options. If you watch our last episode on the proximity, we already touched base to the 2 mostly used indexing strategies, geohashing and quad tree, where they are mapping from complex 2D latitude and longitude indexing into a more efficient data structure. Option 1. Geohashing. Let's quickly recap how geohashing works. The world is divided into a grid with hierarchical precision. Each cell in the grid is assigned a geohash code. Nearby locations share common geohash prefixes, making it easy to filter businesses in the same area. For example, San Francisco, north 37.7749 degree, west 122.4194 degree, mapped to a string of 9Q8YY, and a sushi restaurant nearby, north 37.7751 degree, west 122.4189 degree, mapped to 9Q8YY as well. Since both locations have the same geohash prefix, They're spatially close, making database lookups much faster. Geohashing provides fast prefix-based lookups in databases, so no need for expensive distance calculations. It supports compact indexing as the fixed-length keys are easy to store and query. It delivers hierarchical resolution, which adjusts geohash length for coarse or fine-grained search. But geohashing has its limitations. It doesn't handle unevenly distributed locations. Well, for example, dense urban versus sparse rural areas are different. Also, the businesses near grid boundaries may belong to different geohash buckets. And to address boundary issues, Yelp expands search to neighboring geohash buckets, ensuring that businesses near the edges of a grid aren't mistakenly excluded. The alternative approach is quad tree, where the world is divided into large squares. Each square is recursively subdivided into 4 smaller squares as needed. Businesses are stored in the smallest square that fits their location. Quad tree has its own advantages, such as it can handle non-uniform distributions better where densely populated areas get finer granularity. It is more accurate than geohashing for distance-based queries. But it also has limitations, such as it is difficult to index in relational databases, which requires hierarchical storage. It's more complex queries compared to geohashing prefix lookups. And it needs frequent updates, which are costly. When new businesses are added, the tree may need rebalancing. The two options are a retro to refresh your knowledge point in previous episode. In Yelp, we actually use the Postgres SQL database along with its Postgres GIS extension to help indexing the geopoint from two-dimensional indexing into one-dimensional, and this is actually ingested into the GIS extension part. During your interview, any option is actually feasible for the deep dive, but you can provide enough reasoning on which to select. So what should be the design of database plus geopoint indexing? There are 2 options to consider. One approach is to use PostgreSQL with the PostGIS extension, which provides native geospatial indexing support as we select. PostGIS allows us to store location data in point format, representing longitude and latitude. It also supports polygon data types for defining complex geographic regions, for example, city area of San Francisco. With PostGIS, we can efficiently run geodistance queries to find businesses within a given radius. A typical query might look something like, this query finds all businesses within a specified radius of a user's location, making it a powerful option for handling Yelp-style searches. Another approach is to use Cassandra as the primary data store, combined with Elasticsearch to handle geodistance queries with full-text searches. Cassandra is a highly scalable NoSQL database that provides great write throughput and fault tolerance, but it lacks built-in geospatial support. To work around this, we can store business locations as longitude and latitude in Cassandra using decimal data types. Index the business location data in Elasticsearch, which supports geospatial queries. When a user searches, query Elasticsearch to fetch nearby businesses, then retrieve detailed business information from Cassandra. Both options are great to select. In our design, we use the built-in solution from Postgres database plus PostGIS extension, where the spatial geopoint can be better indexed. As for the term-based search, with the help of Elasticsearch is a good point to generate the inverted index to documents. Now let's talk about the second area to optimize latency, caching. Let's first discuss, what do we cache? First of all, the popular search pattern, such as best burgers in NYC. Second, the frequently viewed business details, such as Starbucks in Times Square. Third, we can also cache personalized data, such as previous searches by the same user to avoid redundant queries. So what caching strategy should we use? We can add application-level caching, such as Redis, to store pre-computed search results for quick retrieval and time to live, short as TTL, to ensure data freshness. We can also add edge caching like CDN, where business metadata, like images and descriptions, is cached at edge locations, reducing backend requests. To update the cache smoothly, we can use write-through caching, which means when a new business or review is added, cache updates automatically. By caching search results, metadata, and user preferences, Yelp can serve millions of requests per second with minimal database load. For the third area to improve latency, we can distribute read workloads for scalability. Since Yelp's search is read-heavy, we distribute queries across multiple database replicas. We can use master-slave architecture for read replicas where primary database handles writes, adding businesses, updating reviews, and read replicas handle search queries, reducing load on the primary database. We could also add shards by regions, so businesses are partitioned geographically. New York businesses in one shard, LA businesses in another, so that each query only hits relevant shards, making lookups faster. The last area that we can improve latency is pagination and prefetch to render search results. This is partially covered in the previous contents, but we want to make it another recap to make it clear. Yelp doesn't return all search results at once. Instead, it paginates results, ensuring smooth and efficient browsing. It applies limit plus offset pagination and returns only 10 to 20 results per page, keeping response times low. It also applies cursor-based pagination for infinite scrolling, and with the use of cursor tokens instead of offsets, it makes faster, large-scale pagination. It also supports prefetching for better UX. It can predict next search results and loads them in advance to avoid delays. With smart pagination and prefetching, Yelp ensures instant search results and seamless scrolling. To recap deep dives in low latency, we can combine multiple strategies. 1. Use geospatial indexes to optimize point and range queries. 2. Caching search results and metadata to reduce database hits. 3. Distributed reads across replicas and shards for scalability. 4th. Pagination and prefetching to optimize user experience. By integrating these optimizations, Yelp delivers lightning-fast search results, even while handling millions of queries per second. Now let's talk about compliance, which is a unique challenge in Yelp's design. This is a controversial topic because we want to prevent abuse. Malicious users could spam a business with fake reviews, either to artificially boost ratings or to damage a competitor. To address this, Yelp enforces a review constraint. But the question is, how strict should it be? Should a user only be allowed to post one review per business in their lifetime? That seems too restrictive. Instead, we can relax the rule to allow one review per business per day, week, or month, depending on Yelp's policy. However, users should be able to edit or update their existing review instead of posting new ones every time. We can enforce this rule at the database level using constraints and indexing. Here's a Postgres query approach to prevent duplicate reviews from the same user for the same business within a specific time window, while still allowing updates to existing reviews. Let's break down the compliance mechanism. Keyword unique with user ID, business ID, and date trunk open parenthesis month close parenthesis created at. This ensures that a user can only post one review per business per month. If they attempt to add another review within the same month, the database will reject it. However, users can edit their existing review, keeping the system fair. Keyword on update current timestamp. This allows review updates, meaning users can modify their feedback without bypassing the restriction. Keyword date trunk open parenthesis month close parenthesis created at for flexible policy. If we want to change the restriction window, we can modify this part with day, week, or year if needed. This is the full content of deep dives. We don't spend much time in scalability. This is because all the non-functional requirements, such as low latency in search, are under the large-scale traffic. So we don't need to spend much time on the general horizontal scalability, such as sharding in databases, or horizontally scaled in stateless services, etc. Let's recap from today's topic. In this episode, we tackled how to design Yelp, a proximity-based search system that must handle millions of users and businesses efficiently. This question is recently frequently asked by OpenAI, Meta, and other top companies. We first cover the core functionalities, such as search for businesses by location, rating, and open status. View business details like contact info, reviews, and menus, and post and update reviews with a rating and optional text. For the deep dives on non-functional requirement, we first discussed high availability and fault tolerance, such as service failures that we solved with load balancing, circuit breakers, and caching. Database failures that we introduced, replication, sharding, and read replicas ensure uptime. Network failures that we discussed, retries, multi-region failover, and CDN caching keep requests flowing. We also went through the optimization in low latency of the system, such as Postgres plus PostGIS for fast location-based lookups, caching frequent queries to reduce database hits, read replication and sharding to scale efficiently, pagination and prefetching for a smooth user experience. We also include a special topic in compliance, so that we can limit users to one review per business per month, but allow edits and discussed how PostgreSQL constraint can help ensure compliance at the database level. That is all for today. Designing Yelp isn't just CRUD. It's about fast, scalable, and resilient architecture. Next time, we'll explore more sophisticated proximity system, Uber, where the location information is fast-changing rather than static in Yelp. If you like our videos, please like, subscribe, and share to your friends. You can also visit us at www.showoffer.io, where you can have more resources for preparing interviews with coaches who are engineering leads from FANNG Plus companies. Stay tuned and see you next time.